Hello all. So welcome to this new video in this course on time series modeling and forecasting using R. So before we start with anything new, so just to give you a short brief as to what we covered in the last session. So currently we are more like exploring the idea of non-stationarity, right? Because again, if you remember, almost 90% of 95% of the practical applications that you see in time series are sort of non-stationary, or they have a non-stationarity kind of a behavior. Alright. So analyzing any non-stationary aspects, let's say trends or seasonal variations or cyclicalities, or for that matter any other pattern, becomes all the more important. Okay. So in this session again, we'll kind of discuss one more non-stationary time series model, which is called as SARIMA. Alright. So SARIMA is a very natural extension of ARIMA. So probably in the last couple of lectures we've explored enough about the model which is ARIMA, right. So if you remember, the full form of ARIMA is called as auto-regressive and then integrated moving average. And then ARIMA is sort of capable of handling any trends in the model, right. So depending on whether you have a linear trend or quadratic trend or let's say cubic trend, one can actually difference the model those many times, right. And then let's say if you want to difference the model once, then the integration power would be 1. So that middle order in the ARIMA model or the ARIMA structure would be 1. And then obviously all the 3 orders correspond to P, D, Q, right. So P, Q correspond to the AR order and the MA order respectively, while the middle order, which is D, stands for the number of times one has to difference the series to achieve stationarity. Okay. Now slightly on the other side, if you extend this ARIMA model to a SARIMA model, so how do we kind of bring in the idea of seasonality? So SARIMA is nothing but seasonal ARIMA. Alright, or in other words, seasonal auto-regressive integrated moving average. So there should be some amount of trend in the data, as well as there should be some aspect of seasonality in the data. Okay. So before we move ahead with SARIMA model, so a few other points regarding non-stationarity once again. Okay. So in general, non-stationary behavior of any time series could be due to multiple reasons, right. So for example, it could be due to trends or let's say unit roots. So just a very brief introduction or kind of a revision about unit roots. So in the last session we talked about unit roots. So if you remember, what do you mean by unit root is that if you solve for that polynomial that you get from the ARIMA structure, and if at least one of the roots happen to be exactly equal to 1, then we have a situation called as a unit root situation, right. And again we saw that unit roots kind of amount to non-stationarity, right, because if you remember, we argued that unit root, what happens is that the current time series value depends on the past value plus some function of random errors, right. So in a given long term or in a longer horizon, such a series won't converge to anything or won't converge to its mean, right. So in that sense, the series would be non-stationary. Okay. So presence of unit roots. The third is seasonality. So the idea of this session would be more about seasonality, because we will expand upon that SARIMA kind of a model structure. And then the last one is changing variance. So of course, if you see some patterns in the variance or variance is not constant, then again it can amount to some amount of non-stationarity in the data. Now again a very quick refresher about what exactly do you mean by seasonality. So seasonality implies that firstly mean of the observations is not constant, right, and it evolves according to a cyclical pattern. So we studied some properties about seasonality in the last session, if you remember. So let's say if you have fixed frequencies and the series is kind of oscillating, then we'll say that you have some seasonal effect or you have seasonality into picture. Okay. And if you remember, the other idea was cyclicality, right. So cyclicality means that the repetitions are not constant. So the repetitions or the frequency of the repetitions may vary. Okay. So you have two different ideas. So seasonal or seasonality and then cyclicality. Okay. Alright, so in fact seasonality could be of multiple types, right. So we will briefly discuss as to what those types are before we kind of go to SARIMA model. Okay. So these are all the types of seasonality. So seasonality could be deterministic, right. So what do you mean by that? So for example, if the seasonality is a constant in the same month over different years, right. So let's say if you have a data and the aspect or the amount of seasonality is the same or constant in the same month over different years, then we will say that the seasonality aspect or the seasonality factor is deterministic. Okay. Now in general, even as we took in the last session, so let's say period of seasonality would be some S. Okay. Now again, remember what you mean by period of seasonality. So period of seasonality means after how much frequency you see the repetitions. Okay. So let's say the period of seasonality is S, then we actually get something like this structure. Alright. So let's say St to the power S within brackets, if it happens to be exactly same as some St plus Ks to the power S, then in such a situation we will say that seasonality is deterministic. Okay. And then this could work for any k. So let's say k could be plus or minus 1 or plus or minus 2 or plus or minus 3 and so on and so forth. Okay. So essentially, just if you look at this equation one more time, so what exactly you mean is that if the current value or the current factor of the seasonality at time point t happens to be exactly same as the factor of seasonality at time point, let's say t plus ks. So t plus ks, what we are doing is we are shifting the lag, right? And then rather than simply taking t plus k as we did earlier, we are kind of taking t plus ks because s stands for the seasonal factor, right? So we can take one example. So let's say if k is 1 and if you have a monthly, let's say temperature data, then generally s is 12, right? So what do you mean by this equation? So this would reduce to something like st and then within brackets s, if this thing happens to be equal to, then st plus k into s would be 12, right? So this would be t plus 12 and then s. So again, if you go to this structure, so essentially what you mean is that let's say the value in January of a particular year, right? So let's say 2023, okay? So the value you have in January of 2023, if that value happens to be the same in January of next year, so let's say 2024, right? Because this, you have a shift of 12 here, right? So Jan of a particular year and then Jan of the next year. Then what would happen if such a situation arises? Then you have a deterministic kind of a seasonality. Now one can actually extend this. So let's say this could be equal to s and then s obviously, and then let's say if you increase this k to 2 now. So let's say if k is 2, then what would happen? This would be nothing but t plus 24 and so on, right? So here clearly one can see that you have gaps of, or you have jumps of 12 between any two consecutive points. So let's say you start here, then t plus 12, then t plus 24, then the next one would be t plus 36, etc. Okay. So in this case, we'll say that you have a deterministic kind of a seasonality. So this is the first type. Then the next type is what would happen if seasonality evolves over time as a stationary process. So what do you mean by that? So let's say again the factor of seasonality is STS, and then assuming that STS is a stationary factor oscillating around some mean. So let's say mu s. Okay. So this is the actual equation. So STS happens to be equal to some mu s plus Vt. And what exactly do you mean by Vt? So let's say Vt is some process such that the expectation of Vt is 0. Okay. Such that the expectation of Vt is 0. And then the idea of bringing this Vt is nothing but, so Vt is a stationary process and sort of brings some variability in this factor of STS, right? Because STS does not depend on this mean entirely, right? So you have this additional Vt portion here. So since you're adding this extra Vt term, so Vt sort of brings in some variability. And then why exactly Vt is stationary? Because Vt is stationary because expectation is 0, so expectation is constant, and so on and so forth. Or for that matter, this is more like an assumption, right? So you can write down assumption. So you're kind of assuming that Vt is stationary, but nevertheless, this Vt, which is a stationary process, sort of brings in a kind of a variability in the seasonality factor or the value of seasonality. Okay. So such an equation will say that you have a certain seasonality for sure, but that seasonality kind of fluctuates or evolves over time as a stationary process. Okay. Now the third kind of a seasonality could be seasonality evolves over time as a non-stationary process. So earlier we saw how it evolved as a stationary process, and now we will see that how seasonality evolves over time as a non-stationary process. Okay. So here again we have this equation. If you take a note of this, so we have STS, which is the seasonal factor, and what we are doing is we are creating a random walk out of that. So can you see the structure here, and then kind of resemble a structure of a random walk. So in a random walk, what exactly you have? So you have something like this, right? So yt equals yt minus 1 plus some error term, right? So this is a very, very typical random walk. So similarly here, what we are doing is we are finding out the current seasonality factor, and if that seasonality factor sort of depends on s t minus s plus some stationary process. But since this is a random walk, so seasonality itself is a non-stationary process in this case. Okay. So in this case, S itself may follow a non-stationary process. So say a random walk as this equation tells you. Now again you have this error term here, which is Vt. So again the idea is that we are kind of assuming that Vt has a expectation of 0, and then Vt again sort of brings in some variability in that seasonality factor. Okay. But thus what would happen is if you apply some seasonal differencing here. Okay. So thus applying some sort of a seasonal differencing actually corrects seasonality in all the three cases. So third one, the one prior to this, and the first one. Okay. So idea is one should always apply some appropriate seasonal differencing. Now again remember what exactly do you mean by seasonal differencing? So seasonal differencing means you want to apply some differencing at a particular lag, right? So let's say lag s. So differencing at lag s would be something like yt minus y of t minus s directly. Okay. So you apply some sort of a suitable seasonal differencing depending on the data, of course, right, to sort of correct seasonality in all the three cases or in all the three seasonality types. Okay. So this is a brief idea as to different kinds of seasonality that one can actually encounter. So seasonality can evolve as a non-stationary process, seasonality can evolve as a stationary process, and if you go back a couple of slides, the first one was if you have a deterministic sort of a seasonality. Okay. Okay. So now in this slide what we will do is we will cover very brief idea about a SARIMA model. Okay. So now again SARIMA stands for seasonal autoregressive integrated moving average, right. So seasonal autoregressive integrated moving average, and then as explained in the beginning of this lecture itself, that a SARIMA model has different parts to it, right. So you should have an AR part, there should be some MA part, and the overall model should be integrated. So there should be some trend aspect and there should be some seasonality aspect as well, right. So hence SARIMA. Okay. Now we have 2 points to note here which are again important. We have covered this multiple times, that if you have a trend aspect, right, so one can actually convert any trends to a stationary series by taking regular differencing, right. So in this case, how would the differencing look like? So one can actually take something like yt minus 1, which is nothing but given by nabla yt, right, and so on. So depending on the strength of the trend, so if you have a quadratic trend or cubic trend or to the 4th power or some other power, then depending on how strong the trend is, one has to difference the series those many times, right. But all such differences are nothing but regular differences, right, because yt minus 1 is in fact nabla yt, and that is nabla yt is a regular difference. Okay. On the other hand, if you want to convert any seasonality to stationarity, then one has to take seasonal differences. Okay. And then the last slide we saw what do you mean by seasonal differences. So seasonal differences, again a quick refresher, means nothing but yt minus y of t minus s directly. Okay. So this would be something like a lag s kind of a difference, right. So you take the current value and then subtract y of t minus s from that, alright. Okay. Now how do you actually arrive at the particular SARIMA model, right. So let us say the initial yt that you had earlier, you make a small transformation to that. So let us say zt is a new process, and then how are you getting to zt? So zt is nothing but through this polynomial applied on yt, or through this operator applied on yt. Now if you look at this operator for a second, so what exactly do you mean by that? So the first chunk in this operator is 1 minus b to the power s whole to the power capital D, and then the second chunk is 1 minus b to the power small d, right. So here you see lot of notations, right. So you see small d, then you see capital D, and eventually you see s, right. So all of you know what s means, right. So s is nothing but the period of seasonality. So if you have monthly data, then s would be 12. If you have a quarterly data, then s is 4, and so on. Okay. Now what about capital D and small d? So capital D is nothing but number of seasonal differences, right? And then this number is usually 0 or 1. Okay. So how many times does one has to difference the data on a seasonal basis, right? And generally speaking, for capturing any practical data sets or practical problems, one need not go beyond 1 with respect to capital D. Okay. And at the same time, what do you mean by small d? So small d is nothing but the number of times one has to take the regular differences. Okay. So this one is seasonal difference. So something like yt minus s, and then capital D kind of tells you that how many times are you taking such differences. And then on the other hand, small d is nothing but the number of regular differences. So something like yt minus 1, which is nothing but nabla. Okay. So to sort of differentiate between the kinds of differencing one has to perform, we are kind of using small d and capital D. So essentially the idea of SARIMA model is to model regular and seasonal impacts separately and then sort of combine into a model multiplicatively, right. So even here you see that we are kind of multiplying these two factors, right. So one of the factors is seasonal, which is the first one, the other factor is non-seasonal, right. So incorporating both these individually and then sort of combining in a form of multiplication. So this is the idea of a SARIMA model. Now how exactly does a SARIMA model look like, right? So the equation is not at all easy, but then just to understand, SARIMA model has lots of individual parts, as you see in this equation, right? So the entire left hand side and the right hand side is a combination of seasonal and non-seasonal parts, both. So again, if you focus here on the LHS, right? So you see capital phi, by the way this notation is capital phi, and then subscript is capital P, and then b to the power s, and then small phi or regular phi, and then subscript is small p, right. So essentially what happens is SARIMA model is kind of a combination of AR structure of a seasonal order, then AR structure of a non-seasonal order, then MA structure of a seasonal order, and then similarly MA structure of a non-seasonal order, right. So can you sort of digest this idea that SARIMA model, since it's a combination of AR and MA, right. So there has to be two orders, right. So P comma Q. But at the same time, since you are controlling both for the trend and seasonality, and then one has to differentiate multiple ways. So seasonal differencing and then non-seasonal differencing, which we also call as regular differencing. So hence we see this capital D and then small d here, right. And so capital phi corresponds to seasonal orders, small phi corresponds to non-seasonal orders, capital theta, so this is capital theta by the way, corresponds to seasonal MA orders, and then small theta corresponds to non-seasonal MA orders, right. So essentially speaking, what you have is you have AR structure and MA structure for both seasonal and non-seasonal orders, and hence we see 4 coefficients. So capital phi, small phi, capital theta, and then small theta, right. And then depending on whether you are having an AR kind of an ordering or MA kind of an ordering, we are using P or Q. So P stands for AR orders, right, as usual, and then Q stands for MA orders. The only extra thing here is that we are using capital P and small p because capital P stands for seasonality, small p stands for regular AR order. Similarly, capital Q stands for seasonal MA order, and then small q stands for non-seasonal MA order, right. So hopefully, so maybe you can pause the video and then just digest this equation one more time as to what exactly is happening here. Right. So again, just to summarize very quickly, any SARIMA model has these 4 paths essentially, right. So capital phi p is the seasonal AR operator of order capital P, small phi p is the regular AR operator of order small p. So when we say regular, this is non-seasonal by the way, right. Similarly, capital theta is the seasonal MA operator of order capital Q, and then small theta is the regular MA operator of order small q. So essentially speaking, any SARIMA model has to be defined using 2 individual triplets of ordering. So small p, small d, small q, and then capital P, capital D, capital Q, and then towards the end we can actually specify the period of the seasonality, which is S. Okay. So again, if you have a monthly data, this S would be nothing but 12. Alright. So hopefully this is clear. So we'll take up an example now, which is what you see in front of you, right. So here what exactly do you see in this table here is the structure of the data. So let's say you have months, given by column. So, the first month, then second month, third month, all the way up to the 12th month. All right. So, let us say January, February, March, April up to December. Okay. So, this would be my December month, and then this would be my January month. Okay. And then at the same time, the first row sort of gives you the years. So, let us say you have R number of years, right. So, you have a monthly data over how many years? So, over small r number of years, right. And one can actually structure the data in a tabulated form, right. So, the first month, then the first year value is y1. First month, second year value is y13, because once 12 of the observations have been exhausted, then the 13th observation corresponds to January again, right. So, for that matter, the entire first column corresponds to data from January over all these R years, right, and subsequently the second column corresponds to data from February over all these R years, and similarly the last column corresponds to data from December over all these R years. So, Y12, then Y24, then the next one would be Y36, right, and then in general the last one is Y12R. So, from this data kind of a structure of the data, we can actually formulate this SARIMA model. Okay. So, here firstly you should understand that period of seasonality is 12 clearly, right, because since you have a monthly data, period of seasonality is 12. Okay. And then how exactly are you writing down the model? So, let us say capital phi of capital P and then B to the power 12. So, why 12? Because S is 12, right. So, you have to raise it to the power of 12, and then small phi small p and then B operated on YT, and on the right hand side we have the MA ordering. So, capital theta capital Q again the same thing. So, B to the power 12 and then small theta small q B operated on the error. So, towards the end you see this single error term, which is ET, which is nothing but the error term, right. So, essentially what is happening, the entire left hand side of the model stands for the AR structure comprising of both seasonal as well as non-seasonal ordering, and the entire right hand side of the equation corresponds to MA structure, which is both seasonal as well as non-seasonal, right. Now, again remember that capital Greek letters, so capital phi or capital theta, they correspond to seasonal ordering, corresponding similarly capital P and capital Q, while the regular phi and then regular theta or small phi and small theta along with small p and small q, they correspond to non-seasonal ordering. Okay. So, in fact, one can actually write down such a model from this data structure. Okay. Now, we are almost towards the end of this session. So, we will talk briefly about what exactly are the pros and cons of, let us say, ARIMA and SARIMA models, right. So, each model has some advantages and some disadvantages, right. So, what could be some pros of, let us say, ARIMA model or a particular SARIMA model, right. So, firstly, any ARIMA or SARIMA model is easy to understand and interpret, right, because if you have both trend and seasonality which is working on the same series at the same time, then how are you kind of combining both the aspects, right. So, seasonal and non-seasonal, then how are you kind of combining trend and seasonality in general, right. So, that idea is slightly easy to understand and interpret. Okay. So, simplicity and interpretability of the models is there. Okay. And then the other pro is limited variables. So, you have a fewer parameters to choose and estimate. So, again if you go back a slide, so for example here, right. So, the set of parameters that need to be estimated are nothing but all these big phi's, all these small phi's, all these bigger thetas, and then all these smaller thetas, isn't it, right. So, once you are able to estimate all these parameters, right, then your entire SARIMA model is kind of estimated, right. So, even if you have an unknown population SARIMA model to start with, but once you estimate all these individual parameters, then your complete SARIMA model is kind of estimated. So, these are some pros, and the last one, what about cons, right. So, let us say exponential time complexity. So, when the values of P and Q increase, there are equally more coefficients to fit, hence increasing the time complexity. So, as one sort of increases P and Q, then one can actually imagine that the equation becomes more and more difficult, right. Second one is complex data. So, there can be a possibility where your data is too complex and there is no optimal solution for P and Q. So if your actual practical data itself is so complex that the algorithm does not converge to a particular value of P or Q. Last one is amount of data needed. So both the algorithms, be it ARIMA or SARIMA, require considerable data to work on, especially if the data is seasonal, right? So for example, using 3 years of historical demand is likely not to be enough, because 3 years would be a short life cycle product, right? But let's say if the outlook is to kind of estimate on a longer scale, right, to obtain a good forecast, then even if you bring in seasonality, such shorter periods are not enough, basically. So these are some pros and cons of the models which are ARIMA and SARIMA, right? So I think in the next session we'll take up some practical ideas of, let's say, fitting some ARIMA model on a data set and so on and so forth, and then see that how it works out. All right. Thank you.